So back to 2.2, the limit. Right. So the picture you have in your mind is like this. Right. The limit. Here's some point C, and here's some value. Here's some value L. Right. The limit. When we say the limit of f of x is L, as x equals to C. You know, the intuitive idea is that, you know, as you evaluate closer to C, then as your inputs get closer to C, then your outputs get closer to L, right? And so the graph is going to look something like this. Okay. You know, as you evaluate closer and closer to C, the outputs get closer and closer to L. And what we said that was equivalent to was being able to always have an answer to a demand, right? So no matter how close the one requires the output to be to L, there's an interval around C in which that is satisfied. Right? There's an interval, and it's actually an interval with a hole in the middle, so a punctured interval. So we don't require anything about the center point, but no matter how close one requires the output to be to L, there's a punctured interval around C in which that closeness is satisfied. Okay, and the picture, right? If you had a picture of your function, you would always be able to. It would be easy enough to check, right? If you had a perfect picture of your function, and somebody said, I'd like your outputs to stay within 1 of L. Can you ensure that all the outputs stay within 1 of L? And you say, oh yeah, look, here's L plus 1, here's L minus 1, and I see that if I take this punctured interval here, then all my outputs stay between those two bars, right? Stay between L minus 1 and L plus 1. Okay. And if somebody said, I'd like you to stay between these two, I'd like you to stay between L minus 0.2, L plus 0.2 and L minus 0.2, you'd say, oh yeah, I think I can do it. Right? I find this in this interval, all my outputs stay within your bars, right? And you see that, at least on this picture, it sure looks like no matter how tight the tolerance given, you can always find a place where that tolerance is satisfied. Okay, is that everyone okay? Okay, so the picture, that's how you do it with a picture. And then you can also do it algebraically. So algebraically, in the case of lines, so case of linear f. So somebody let's just make up a linear f. Somebody make up a linear function. F of x is 5x. 5x minus 2. 5x minus 2. I'm going to make it negative 5x minus 2 because we haven't done any negative slopes, and just to illustrate. Okay. And what's your c going to be? What are you going to take as your c? 25. What? 0.5. All right. Why is the fun? Fine. Okay. So where are we? We're at negative point. It's not going to make it harder, but it will make it more complicated looking. Okay. I'm going to make it some other whole number. 4. Okay, thank you. Okay. So then you already know inside your head, right, that this is going to be negative 22 as x approaches. As x approaches 4, the limit of the thing is going to be 22. Okay, that's secret. Okay, you don't pretend you don't know that. Okay, but somebody says, you think it's negative 22, and somebody says, are you sure that it's 22? So the question that person asks you is, given any tolerance, given a tolerance say 1, can you find an interval, like a distance delta, so that if the distance of x to 4 is less than delta, then the distance of f of x to negative 22 is less than 1. Okay. So somebody's saying, you said you're claiming that the limit is negative 22. Well, can you play the game for me? Let's play the game. I'd like you to stay within 1 of 22, negative 22. Okay. I'd like you to stay within 1 of negative 22. Can you find a place where that happens? And you say, okay. So you start thinking. You say, well, let's see. So here's how you do it algebraically if you didn't have a graph. Okay. If you didn't have a graph, you say, well, let's think. I want f of x minus 22 to be less than 1. I want this to be less than 1. That's the same thing as saying negative 5x minus 2 minus, I'm sorry, plus 22. Plus 22 is less than 1. Right? Because it's minus 22. Right? My distance, I want the outputs to be within 1 of minus 22. Right? So it's the distance to minus 22 has to be smaller than 1. Okay? And so you'd say, well, okay, that's the same thing. That's the same thing as saying negative 5x plus 20 must be less than 1. Right? Just negative 2 plus 22 is 22, is 20. And that's the same thing as saying I'm going to factor out a negative 5. I get, let me slow it down. So you get x minus 4. So I factor out a negative 5. Right? Again, we're just using elementary school arithmetic. Okay. Now we do something that's not elementary school, which is we use the fact that the absolute value of a product is the product of the absolute values. Right? The absolute value of A times B is the absolute value of A times the absolute value of B. Okay? And that is the same thing as that I want this to be smaller than 1. Okay. And that gives you the clue. That gives you the clue about what your delta should be. Right? What you see is that f of x minus 22 being less than 1 is actually equivalent to x minus 4 being less than a fifth. Right? Those are actually the same statements, right? Just simplified. One is the simplification of the other, right? And so you'd say, okay, that'll do it. So I take as long as the distance of x from 4 is less than a fifth, I know that the tolerance of 1 is satisfied. Right? Because if this is less than a fifth, then I know that 5 of it is less than, I'm just going to go backwards, is less than 1. That's the same thing as saying that the absolute value of negative 5 x minus 4 is less than 1. That's the same thing as going back. You get negative 5x minus 2 plus 22 is less than 1, which is what you want. Right? Okay, so that 1/5 worked, right? You say, as long as my inputs stay within 1/5 of 4, my outputs are going to stay within 1 of negative 22. Yeah, Mariah.
Wait, but what if C was like 3?
What if C was like 3? Then it would still work out. So so you'd have in that case the limit of f of x as x approaches 3 would be negative 17.
Yeah, I see.
Right, and then it would still work out.
Yeah.
Still work out. Okay. Okay. Now, what if the tolerance is 0.1? What if the tolerance is 0.1? Does anything change here? Basically, the whole thing, we just put 0.1s all the way down, and what is the distance going to be at the end? 0.1 over 5. As long as we're in 0.02, excuse me, as long as we're in 0.02, within 0.02 of 4, then our outputs are going to be within 0.1 of negative 22. Okay. What if the distance is 7? The tolerance is 7. What am I going to get over there? What's the distance? 7 over 5, right? Okay. So then what you see is that you can do it for any number, right? You can do this for any number, any positive number. So if somebody says, what about for some general number? Then what's the distance going to be? Epsilon going to be epsilon over 5. Okay. And this is how you show that. So if you can do it for any epsilon, and we see that we can, then the limit exists. Okay. So that's the game, right? So given any epsilon, take delta to be epsilon over 5, or something smaller than epsilon over 5. Anything smaller would certainly work as well. Then, if x minus 4 is less than this epsilon over 5, we see that, again, 5 x minus 4 is less than epsilon. Which is equivalent to negative 5 x minus 4 being less than epsilon, which is equivalent to, negative 5 x minus 2 minus plus 22 being less than epsilon, right? Which is to say that f of x minus 22, plus 22 is less than epsilon. Right, so we're able to find a delta. No matter what epsilon you're given, you can find a delta that works. So the limit of f of x is actually negative 22 as x approaches 4. So that's the game. That's the game for linear functions. Yeah.
Regardless of the negative slope.
Yeah.
Okay.
Yeah.
Cool.
Yeah.
Why does epsilon have to be greater than 0?
Because we're talking about a distance. We're saying we want the distance to be smaller than some number. If we say we want the distance to be smaller than a negative number, well, then there's no such distance.
Okay.
Right? When we talk about distance, we mean positive numbers. Yeah. Mariah?
But what if you don't have the limit? You wouldn't be able to prove it, right?
What if you don't have the limit? Yeah. Then it's a little bit trickier.
Okay.
Yeah. But you maybe make some guess as to what it is, and then you show that it actually is that limit. So in that case, there's an extra bit of a problem.
Okay.
But at least the main thing here is that I'm hoping that you get the idea of what it means for the limit to exist. And we're showing it in the simple case of linear functions. We're not going to do it in anything harder than that. At the University of Chicago, they always had like one night where a graduate student would come in and show everybody how to do it for quadratics. Like there was this one lecture, and he'd come in dressed as some like old Russian person, and he'd give this lecture and on how to do it. But I don't think there's much point in that. The main thing here is for you to understand what it means for a limit to exist. It means that given any tolerance, you can find a place. Given any closeness to this number, you can find a place where you can make your function that close to that number. Okay. Yes, Stefan.
Sorry, I don't quite understand. Could you go like step by step just so like we...
Going backwards?
Yeah, like I see in the end that what you get for what the tolerance has to be, you just like do the reverse of what you did to x in the equation.
Yeah.
But I don't understand the thought process and how that part explains the...
So remember the game. The game is, given some tolerance, can you find a distance to 4 so that the function is within that tolerance of the limit? Right? That's the game. Somebody says, I'd like you to stay within a certain tolerance of this number. Can you do it? Can you find a place where that happens? And it turns out, via your scratch work over there, that you figure out a distance. Here it is. Turns out that epsilon over 5 will ensure that the function, the distance, turns out that if your inputs are within epsilon over 5 of 4, then your outputs will be within epsilon of negative 22. Right? And how you show that is you say, well, look, if my distance, if x is within epsilon over 5 of 4, well, then this is true. By multiplying both sides by 5. This is true, right? Because this is the same thing as this thing. Haven't changed anything. Right? This is true because this is the same thing as this thing. Right? And this thing here is f of x. Right? So what we see is that as long as my values are within epsilon over 5 of 4, my outputs values will be within epsilon of negative 22. In other words, I can make, I can satisfy any tolerance you give me. In other words, the limit is negative 22.
So you use the absolute values and the function has to be either minus the limit if it's a positive number or plus to show the distance from that. Then you plug in the function and then you keep simplifying it until I don't get it.
Okay. Do you understand? Okay. Okay. Let me try and figure out what you don't understand. That's part of the game here. So, what's a limit? What does it mean for the limit to exist?
That's to fall within the brackets of when you give the epsilon.
Right. So here's your function. Here's negative 22. Here's 4, and you want to show that if somebody gives you a tolerance here, you can find a place around here where that tolerance is satisfied. Okay. So. So, right, so you want I'm either excited or I'm angry. I hope I'm excited. Okay. You want to find a distance to 4 so that if x minus 4 is less than that distance, then f of x minus 22 is less than epsilon. Right? You want to be able to do that for any epsilon. Right? Okay, and then you do it. You say, okay, right. So this is the distance, right? It's saying the distance of x to 4 must be less than delta. You want to find a distance delta to 4 so that if this happens, then this happens. Okay. You do your scratch work, and it turns out that delta being epsilon over 5 will do. You do your scratch work and you find it out. Take delta to be epsilon over 5. Okay. Then you notice that if this is less than epsilon over 5, then you go back to this thing, then f of x minus 22 is less than epsilon. Right? So no matter what epsilon you're given, just take your delta to be epsilon over 5. And so that tells you that your limit is negative 22.
How did you get to the take delta to equal 3 over 5?
Epsilon over 5?
Yeah, sorry, epsilon.
That was the sketch work that you did over here,
Yeah.
right?
Okay.
So you look at the f of x minus negative 22, and you see what that out pops a delta, right? Out pops a delta. When we did it for 1, the delta turned out to be 1/5. When we did it for 0.1, it turned out to be 0.1 over 5. When you do it for an arbitrary epsilon, it just turns out to be epsilon over 5.
Okay.
Okay?
Thank you.
You're welcome. The difference between, I think, my angry face and my happy face is not that substantial. So, maybe it's hard. Yeah, but I'll tell you the tell. If I lick my lips, that means I'm extremely angry. If I go like this, then just run away. Run away that way. Okay. So anyway, I hope you get the idea here. What does it mean for the limit? What does it mean that the limit exists? It means that you can make, if somebody says, I want you to be this close, you can find a place where you are that close. That's it. Okay, so there are a couple of things that happen that are consequences of this definition. The first is that limits are unique. Like you can't have two numbers that both work as the limit, right? If somebody says the limit is L, and somebody else says the limit is M, then those numbers are forced to be equal to each other. Okay. Yeah.
What does it say, like next to the?
Say the limit
Oh, no,
of
it's on
f
the
of x.
box.
Limits are unique.
Yeah, what does it say next to that?
Limits are unique. ... Semicolon. Theorem.
Yeah.
Sorry. Theorem.
Okay.
Sorry. Theorem. Limits are unique. So if there are two things that people claim to be the limit, well, they're going to be the same thing. You can't have two different limits. And so let me sort of roughly tell you, you can sort of see why that's going to happen. Right? If there's two numbers that people claim to be the limit, well, then if you would say, well, I'm going to take this as my tolerance. If this is my tolerance, then I can find a neighborhood where all the values lie within that tolerance, and they're far away from M, right? And so this M couldn't possibly be the limit. If there were two different limits, you'd end up with some sort of logical contradiction, right? Right? Because you'd say, I'm gonna, since M is the limit, I'm gonna make all my outputs, this close to M, and I'm also gonna make all my outputs this close to L, right? But how could that happen? That would mean that your outputs lie in here, and they also lie in here at the same time, but those places are disjoint. Okay. So anyway, the definition forces limits to be unique. So there are other consequences. Consequences of the definition. So the next one I think you'll like a lot. Limits and arithmetic. If the limit of one function is L as x approaches C, and the limit of another function is M as x approaches the same point, then the limit of the sum function as x approaches C is going to be what? is what?
Of G? No.
If the limit of f is L and the limit of g is m, what's the limit of the sum going to be?
L plus M.
L plus m, right? As you expect. L plus m. Similarly, the limit of the product function f times g is going to be L times m. The limit of the quotient f over g is going to be L over m, as long as m is non-zero. And the limit of any number times f, right? So say alpha is some real number. It's just going to be alpha times the limit. Right? So it's sort of obvious. Obvious statements. Okay, that things that you would hope to be true actually turn out to be true. Okay, and we're not gonna prove them. I'm just gonna tell you that the definition forces these things to be true. Okay, so we'll just use this as a tool. Okay. So, for example, the limit of x as x approaches some value c is what? What's the limit of x? I think you're copying. What's the limit of x as x approaches c? C, right? Right. As x approaches c, x goes to c. So by number 4, the limit of 5x as x approaches c is what? 5c, right? Right. You can pull the constant out, right? That's what this is saying. If you're multiplying by a constant, you can just pull the constant out. You get 5 times the limit. That's 5c. Okay. By number 2, say, what's the limit of x squared as x approaches c? C squared. Right? It'll just be the limit of x times the limit of x. Right? This is going to be the limit. The limit of x times x is the limit of x times the limit of x. Well, it's c times c. Let's just say c squared. Right? And so, in particular, we get x to the n, then it's going to be c to the n. Right? Now, if we use number 1, the limit of 5x to the n, x to the n plus, let's say like x plus x squared, x goes to c, what's that?
C plus C squared?
C plus c squared, right? Because the limit of a sum is just going to be the sum of the limits. Oops. C plus c squared. And so what you see is that given any polynomial, we see that given any polynomial, the limit of a naught plus a1x plus a2 x squared plus a n x to the n as x goes to c. Right? Given any polynomial a naught plus a1x plus x squared plus a n x to the n. Right? Yes, so given any polynomial, what's the limit of the polynomial? Just be
C naught plus C.
no. It'll be a naught plus a1 c plus a2 c squared plus a n c. Right. using all the using properties 1, 2, and 4. Right. 1, 2, and 4 all together. Show you that to find the limit of a polynomial, all you need to do is just plug in the value. Right. So polynomials. Somebody asked earlier, what kind of functions can you find the limit by just plugging in the value? Well, here's one answer. Polynomials will do that. You can do that for polynomials, right? So for polynomials, the limit of p of x as x approaches c is just p evaluated at c. Okay, yeah, Mariah.
Wait, so there's no subtraction? Like, could you subtract?
You can subtract. Yeah, so these are just numbers. They could be negative numbers. These alpha, right? These a sub I are all just real numbers. One writes them as plus, but they could be plus negative numbers. Okay. So right, if I ask you the limit of x squared plus x plus 5 as x approaches 1, you can just say, well, by the theorem, all I have to do is plug in 1 and I get 7. Okay, but by the theorem, I know that the limit of a polynomial is just the polynomial evaluated at 1. So just evaluate at 1 and get 7. Okay. This is great, right? Because then you don't have to do all that epsilon delta stuff for these guys. Right. Using something that I just erased, the quotient property, using property 3, we see that the limit of if p and q are both polynomials, then the limit of p over q as x approaches c is just going to be the limit of the top guy as x approaches c over the limit of the bottom guy as x approaches c. Right? That's to say p of c over q of c, as long as q of c is non-zero. Right, so we said that the limit of a quotient is just the quotient of the limits. Right? The limit of a quotient is just the quotient of the limits. Right? So if we have one polynomial over another, right, then the limit's just going to be the limit of the top guy over the limit of the bottom guy. Right? So to make it concrete, if I ask you if I say, what's the limit of this? What is the limit?
7/2.
Can be 7/2, right? All you need to do is take the limit of the top, which is 7, over the limit of the bottom, which is 2. Stefan.
What if q of c equals 0?
If q of c equals 0, then you don't have an answer.
Okay.
Yeah. Then, it's possible that the limit doesn't exist, or it might be that the limit exists for some other reason. But you can't conclude. You can't conclude from the theorem. Okay. So right. So we found another kind of function for which we can just evaluate it. Right. What we saw earlier, that we can just evaluate to find the limits. We just evaluate polynomials. Also for rational functions. Right. If you have a polynomial over a polynomial, then you can just evaluate it. So both of these functions are of the type that you can just evaluate them to find the limit. Okay. So one can use the evaluation trick to find the limit of polynomials and rational functions. Here is something called the squeeze theorem. And it will be useful in finding limits that are a little bit more tricky. Okay. So here's the picture. You have two functions, f and h. Okay. F is the lower guy, h is the upper guy. Okay. And they have the same limit. They have the same limit at c. So you have two functions. The limit of f as x equals to c equals the limit of h as x equals to c. Okay. If there exists a third function that's trapped between those two, so if there's a third function g that's trapped between those two, then what do you think is going to happen?
The limit's also going to be.
The limit of that guy is also going to be that. Even if the third guy is very, very wide, maybe the third guy oscillates quite a lot. The third function oscillates tremendously or does crazy things. Okay? But because the other two have a limit there, the third function is forced to have a limit. So the limit exists. As x equals to c and equals f. Let me give you an example. F of x is x sine 1 over x. F of x is x sine 1 over x. This is a crazy looking function. It looks something like this. Looks something like this. If you graph it out, that's what you'll see. Oscillates a lot. But if somebody asks you, what's the limit as x goes to 0, what's the answer? Just from looking at the picture. It'll be 0, right? It'll be 0. And the way you'd show this using the pinching theorem is like this. You'd say, well, observe x sine 1 over x is smaller than the absolute value of x. Smaller than or equal to the absolute value of x. Right? Here's the absolute value of x function. Right? And I also know that this thing is bigger than negative the absolute value of x. Okay. And I know that the limit of the absolute value of x is 0 as x approaches 0. Right? And that the limit of negative the absolute value of x is 0 as x approaches 0. Right? So I have something smaller whose limit goes to 0, and I have something bigger whose limit goes to 0. And so the one in the middle is forced to have also the same limit. So I know that the limit of this exists and equals 0. Am I right?
When you say function's bigger, does that just mean the outputs are larger?
Yeah, just the as numbers, right? If I put in the absolute, if I put in a 2 here, I'm going to get something bigger than this.
Okay.
That this 2 sine 1 over 2 is trapped between negative 2 and positive 2. Okay. So next time we will use the pinching theorem to get some interesting facts, some useful facts. Okay, but that's it. That's it for today. Take a look. I'd like you to read. There's a small section on one-sided limits in this section. Please read that yourself. I'm not going to talk about it. Just read it.